Good day, ladies and gentlemen. Last week I tried to walk you through the applications of a difference equation, and I do recall that we discussed three main applications. The lagged income model, the Cobb model, and then the Harrod's model. I believe you've taken your time to go through that lecture very well, and of course the assignment that I gave you. Now, in this lecture, I'm trying to introduce you to linear programming, and then you will see how, trying to optimize or have an optimization with different constraints, and in specific terms, when the constraints are inequality in nature. This is the overview of what I intend discussing with you, and specifically, I have this outline. Now, when we talk about linear programming, what are we talking about? Recall that when we discussed, I think the first or second lecture, we talked about optimization with constraints using the boarded Hessian, where we have an objective functions, and then where we have constraint functions that were inequality, that had equal signs. And you remember that we use the Lagrangian, to solve problems of this nature. Now, the problem we have here is that, and in many cases, we considered a situation where we have only one, constraint function. So it was quite easy. Set out a Lagrangian function and off you go. But we are now adding on. And the addition is that, assuming we have an objective function, but then we have more than one constraint function, and the constraint functions are not, made up of equality sign, but inequalities. How do we go about this? So that's what we'll be doing. We will try to look at how to optimize functions when you have more constraints and when the constraints are inequalities, right? So this is the vein of our discussion of linear programming. Now, there are so many approaches to trying to formulate linear programming, problems. At our level, we will try and discuss more or less the graphical approach to solving linear programming problems. I made an attempt to use the other method, that is a simplex method, but I think it's a little demanding maybe in our last lecture. So I may cut it off, for those of you who have time can take time out of your busy schedules and then look at how you use simplex also to solve linear programming, in addition to the graphical method that I will be detailedly discussing with you. Now, the applications of linear programming is quite vast, especially in production processes, right? And we will look at specific application when we solve problems. A little activity for you, just for you to stretch. Now, let's look at the system of linear equations in 2 dimensions. Those of you who did, core maths, you may be familiar with linear equations of this nature. So these can be constraints, and you have an objective function of this nature. At our level, we will always consider that we are operating in the positive, x and y Cartesian coordinates, where x is always positive or equal to 0 and y is always, positive or equal to 0, because in the other sectors, normally, interpretation is quite vague, and for economists, we are not much interested in those areas. We only want to talk about positive, values, or let me put it, non-negative values or constraints. If you look at, so the first thing you have to learn how to do is to know how to plot an inequality. When you have any equality, right, it defines a region. Any inequality defines a region and not a straight line. So we are going to look at how to plot inequalities and indicate or shade the region which that inequality defines. Having done that, then we will look at how to optimize the function with the constraints that we have already tried to know how it behaves. So if you take this equation or inequality and you want to plot it, you just first turn it to an equal to sign, as you can see over here. All right, as usual, when s is equal to 0, y is equal to what? When y is equal to 0, s is equal to y, what? And then you get this line. So this is the line, 5x plus 3y equals 30. Now, the region that defines this inequality will either be here or either be there. So what you do is that you take any value here, put it into this equation, and see whether it satisfies it. Then, if it satisfies, it means that point here satisfies this region, and therefore the whole region here is the region defined by the inequality. I like putting 0, 0 because it makes your evaluation here 0, 0. So here at this point, x equals 0, y is equal to 0. So when you put 0 here, put 0 here, you get 0 being less than 30. And it's really true that 0 is less than 30, and therefore the region that defines this inequality is this region. And you can see it plotted here nicely. So this is the region defining our inequality in question. Now, there is also one thing you need to know. Usually, when this is a straight inequality sign, we allow this line to be dotted line. All what it means is that the region does not include the points on this line. But when it's less than or equal to, right, then we use a thick line, showing that the line itself is part of the region. So know the difference. Whenever it's a straight inequality, we use a dotted line. Whenever it's a very loose inequality, like less than or equal to, then we use a thick line. Now, and one thing I would also like you to know is that we have defined this in the region where x equals 0, x is greater than or equal to 0, and this is this area. As I said, we are interested in what happens in the positive artant, right? In the positive area. Or what happens here, we are not much interested as economists, and at our level too. So here, I have plotted these two inequalities, what we have over here and what we have over here. So this is the first line, this is the second one. Now I want a common region that satisfies the two. All right, so what it means is that I should take a point here, put it into an equation and see whether it satisfies it or not. And we can see that there's a region that satisfies. So it means any point in this region will satisfy these two inequalities. So it means that the region here defines the inequality. In many cases, if you want to know the point over here, all what you do is that this equation and this equation, this inequality and this equality, now it's an equation. Once on the line, it's an equation. You solve the simultaneous equation, and the point here, we're able to know the point x and the point y. Good. Please take your time and try to plot these inequalities and try to indicate the regions, right? We will be dealing with two main problems, maximization problems and minimization problems. In a maximization problem, we usually have the inequalities being less than something. And of course, the fact that we are operating with x and y being what? Positive. Now, let's look at all these in a specific example. If you look at this example, it's about a furniture company that produces a certain output using labor, using machines, and the combination in which it uses that machine, right? And our objective is to know how it has to allocate the time to the company according to these labor and machines to be able to maximize. So if we want to reduce the question to inequalities, this is what we are going to have. So these are the inputs, the labor and machine, right? If it wants to produce a kitchen set, it needs that and it needs that. If it's producing a bathroom set, it needs that, it needs that. So these are the contributions to profit. So a unit of that one contributes this to profit, and you need this one. And these are the constraints. That is our available capacity. Okay? These are the constraints or the available capacity. So in the question that we have over there, if you want to put in a table form, this is what we get. So the next point, we have to express it in inequalities. So what it means is that we are optimizing or finding the maximum of this function subject to these constraints. All right? Subject to these constraints. With a graphical solution, we have to assume this non-negativity constraint because we are interested in only what happens in the positive side of the Cartesian coordinates. So as I said earlier, we plot this line, we plot that line, and we can see that any point over here in this region satisfies this equation and also satisfies this equation. So it means this region defines these two inequalities. So out of these two inequalities, the question is at what point in this region will give us the maximum point? Okay? What point in this region will give us the maximum profit? There's a theory that says that if there is going to be a maximum, then it's going to be at the vertices. So if there is going to be a maximum for this one, it will either be here, or be here, or be here. It will not be in the inner, inner areas of the defined or the feasible region. So all what you need to do is that you have to know the vertices, okay? You slot them into this equation, and then you know which one gives you the maximum. This vertex here, we don't know. It means we have to solve this equation and this equation simultaneously to obtain this vertex. But this vertex, we can straight away deduce it from the equations. So when we solve these two, so the first one at E, there's a point, we have to solve this one. We get these as the points, and then we also have this. So we have 3 points, okay? We have 3 points. So we put the points into the equation, and we see that the maximum is at 144 at the points here and here. So it means that the maximum profit will be obtained if the company uses at the point F, and really if you look at the graph, the point F is the point that we have over here, this point. So if it uses this amount of inputs, this amount of the first input, this amount of the second input, then it is going to have the maximum profit, which is, as you can see over here, 144. I have another example here. In the same way, I would like you to take your time and then go through this example in the same way as we did with the first one. Now, let's look at the solving a minimization problem. With a minimization problem, in many cases, the constraint function, that is a constraint inequality, is a maximum. And of course, we also consider the non-negativity conditions that we have here. And let's look at it as a specific example involving a horticulturalist who is trying to apply, mixed fertilizer, different amount of, potash. So this is 2 brands of fertilizer, and this is the component of the different, fertilizer, potash, nitrate, and phosphate that he needs to combine to form brand X and brand Y. And these are the constraints that he has got in the potash, and this is more or less the function that is supposed to optimize. So in a tabular form, we get this, which we can transfer into inequalities as this. So this is the cost I think he's trying to minimize. And then we have these equations which are generated from these equations, this area, right? We generate it from here. So we go on with a solution. First of all, we plot these constraint functions together in the positive, sector of the Cartesian coordinates. And it means that when you plot the 3 lines, we have this. So The region here is the region that defines, the common region for the three inequalities. So we have how many vertices here? A, and then we have here to be B, and then C, D. Okay, A, B, C, D. We need to, as I said, in this question, if there is going to be a minimum, the minimum will be obtained at the vertex, either A, B, C, or D. It shouldn't be obtained here. So we need to know all these points, okay? And where we need to solve simultaneous equations, we have to do that. And we come to see that this is the point A, this is the point B, this is the point C, and of course, there's a point, the point D is there. So we put the point into this equation, and then we come to know that the minimum cost, so these are the costs that we have, and the minimum is over here at the point B, and it means if he wants to minimize costs, it should combine, the three sort of fertilizer in these equations, in these proportions, to be able to have the minimum cost. I have an activity for you here, and I would like you to use similar approach to work out this activity, and let's discuss it if you have a problem at the chat room. Thank you.